All right, so let me end the poll and show you the results. Okay, so we have 6, it's quite widely distributed, okay. So the correct answer actually should be A, okay. So this one is not correct, okay. So we say that the probability must be symmetric. So in the infinite quantum world, it's like this one. Okay. So this is 0. This is W, for example. We know the ground state is like this. And this is symmetric. Okay. But the first excited state is like this. The psi is anti-symmetric. Okay. So actually we have Px equals to P W minus X. So it's symmetrical. But the percent Mx equals to -1 to the power M minus 1 percent M W minus X. Okay. So it's symmetrical or anti-symmetrical. So in this case, it's symmetric. But this one is anti-symmetric. Okay. So this one is not correct, okay? So you could symmetrical or anti-symmetric. Okay, so the first state is symmetrical, and the second is anti-symmetrical. And then another state is symmetrical again, okay? And then if you consider higher states, it will be anti-symmetric. Okay. So this is psi 4. This is psi 3, okay? Right, so they alternatively to be symmetrical, anti-symmetrical, symmetric, anti-symmetric, and so on and so forth. Okay. And then another one is B. This one is correct actually. So it's not a superposition of 2 plane waves. It only within the quantum world it's a plane wave. Okay. So if it's a wave function like this one, but outside this. It's just 0, okay? If it's a plane wave, it should be also oscillating, the same outside. But of course, because the wave function must be 0 outside this quantum world, so it's not really a plane wave, okay? A superposition of 2 plane waves, okay? So it's a standing wave within the quantum world, but it's not a superposition of 2 plane waves. So that's one thing we need to clarify. And this one, any function defined within the quantum world can be expanded by this one. This actually is correct because it's just a Fourier series. Okay, expansion. Okay, so this also is called the completeness of percent M. Okay, so that means any function defined within the quantum world, that means it's 0 outside, can be expanded. As a linear combination of these eigenstates. And this one, I think all of you have done this one correctly. All the eigenstates are orthogonal to each other, so the overlap of them, integrate should be 0, okay? And this one is also correct. So if we have a superposition of this one, we have to say that, and then as time, okay, if you look at the time evolution, so this will be E2 minus I E1t over h bar. This one will be E2 minus I E2t over h bar, okay? And then the interference between the 2 wave functions at different times actually will give you destructive or constructive interference at different regions. And then if you calculate look at the probability distribution, it's a wave packet oscillating in the quantum world from left to right and then back to left. And therefore, the value of this expansion values, the value of this position, or the dipole actually will oscillate with the the frequency, and you can see that whenever t is integer multiples of 2 pi over omega 2(1), and then the 2 phases actually will be the same. Okay, so that means they will be just back the same as the original state at t equals 0. Okay, so that means the period is 2 pi over omega 2(1). That means the angular frequency is omega 2(1), given by E2 minus E1, the energy difference divided by h bar. Okay. Right. So this is what we have learned last time. Okay. So now we can actually give you a few remarks on the general properties of one-dimensional states. Okay. So the first one, I want to say that if you have this boundary states, okay, this boundary states should be a real function. Okay. Let me say. So there is a real function. You know, the definition of a quantum state is always up to a global phase factor. A global factor, okay. Right. So let me try to show you why. Okay. So this actually gives us a lot of understanding of the boundary states in one-dimensional space. Okay. So you know that if we define the probability distribution of this state, that's of course because this is stationary state, it will be just like this one, right? Okay. So this should be the stationary state. So that means if we do the differential of this with respect to time, okay, this should be 0 everywhere, right? So this means if we do the differential with this one, p x t, that will be always 0, okay? Right. So it's because of this state is stationary. But on the other hand, we also know that there is probability conservation, right? So that means partial t, this pxt plus the divergence of the current should be 0. This is very easy to understand. So if you have the change of the probability, okay, and then of course you're going to have a flow of the current, right, to compensate this one, so that the total probability is conserved. So this, of course, will immediately tell us, you know, for the stationary state, you should have this one. Okay. So in 1D, of course, that simply means partial x and j equal to 0. Okay. And this j is defined as h bar over 2mi, and the wave function per psi mx and d over dx per psi minus d over dx per psi star m and per psi m, right? So that's the definition of this one. Okay. Right. And also you know that at x equals to plus or minus infinity, you must have j equal to 0, right? Because there is a boundary state. This is the right. If it's a boundary state, then you shouldn't have a current flow at the infinite, right? Okay. So from this one, you can know that j just simply equals to partial j partial x. You do the integration from minus infinity to any position, right? And since this one is 0, so that means this one must be 0, right? So that means j is 0 everywhere, okay? For the one-dimensional boundary state. All right. And now we can put this back, okay? We are trying to prove this per psi m is a real function. Suppose it's not a real function. So let's write this per psi m as the probability, you know, square root of the probability, okay? This is a real function. And then times the phase factor. This depends on this one, right? So let's check this one. So I can write down this one as, for example, say just percent nx e to I phi x, right? And let's look at the differential of this one. So d over dx of percent m. We just have two terms. One is d over dx percent mx, right? The differential on this absolute value of this function, and then times this phase factor. That's supposedly depends on the position. And then you also have another term. Okay, and then times percent mx, right? Okay. I know you can insert this one into this one. You find the G actually. So let's look at the G. So you have this one. So you put this to this. You find that the first term will give you simply just percent m d over dx percent m, right? That's the first term, because the phase factor will just cancel each other. And the second term will be just percent m modulus squared e minus I phi x d over dx e I phi x, right? So you look at this one just give you the differential of this phase factor. So that equals, so you have two terms. The first one is the one that, okay, let's, so this first term will be simply just 1 over 2 d over dx percent m modulus squared, right? And then the second term will be just percent m squared. And then that's a phase factor I d over dx phi x, right? Okay. And then you look at this one. This one is nothing but just the complex conjugate. So you have percent m d over dx percent m complex conjugate. It's nothing but just 1 over 2 d over dx percent m squared minus percent m squared I d over dx. So you have a two part. One is a real part, another is an imaginary part, okay? And then you take the difference. So if you take the difference, this one minus this one, so G will just equals to h bar over 2mi. And the real part will cancel each other, so we only have the imaginary part. So that is I percent m modulus squared d over dx phi. And then minus, there's a minus, so you get a plus, right? And I phi m modulus squared d over dx phi. So again, these two terms now become the same, right? So the result is simply phi percent m modulus squared over 2m. The 2 will cancel, right? So you got a h bar over m and the phi m modulus squared d over dx phi. And this one must be 0. But this term is always positive, right? So that means you must have d over dx phi equal to 0, or phi equals to a constant. Right? So if phi is a constant, of course, and then up to a phase factor, so it's a real function, times e to I times phi. This is a constant, right? So that means we do have %m is a real function up to a global phase factor, right? So this one shows that you can always write down the bound states of bound eigenstates of one-dimensional potential as a real function, okay? Because you can always multiply a global phase factor to a state without changing the physical meaning, okay? So this is one thing that we can prove, right? So it's a property of the bound states. And you can see that the important thing that we have used is that is 1D, so that you can do this differential integration, okay? So it's important that you have this one to be 1D, okay? Right? Okay, and then the second property that, and this percent nx is non-degenerate. What does this mean? That means, for each EM, there is only one unique %m, okay? It's actually quite easy, okay, to prove this one, because we know that %nx is a real function, right? From the properties we have just studied a little bit earlier. And then you know that it's a bound state, okay? It's a bound state. So that means this one has a maximal, okay? But it's a real function, so that means this %m has a maximal. So there is a point x0, for example, and this differential of this wave function must be 0, right? Because it has maximal. So if you have a wave function like this one, for example, and then this point, so you must have %x equal to 0, right? Or this point, it doesn't really matter. There's at least one point you have, a wave function that's maximal, a local maximum, right? So that means you must have this point is, and then you know that we must have %x, then can be written as %x0, and then plus the integration from 0 to x partial x dx, right? Okay, and then you can using the Schrodinger equation. So this one can be obtained by Schrodinger equation, okay? So by Schrodinger equation, you find that then you have this one will equals to x0, okay? By time-dependent Schrodinger equation, okay? You find that the partial x will equals to partial x x equal to 0 plus, of course, right? And then this one equals to, this is 0, right? So plus, but this one, according to Schrodinger equation, is going to be just v minus e % and dx from x0 to x, right? So you put this back into this one, so you obtain that this is going to be v minus the energy times 2m, sorry, times 2m over h bar squared, times 2m over h bar squared, and then times %, say y and dy. I know that, so you can see that as long as you know this initial value of this one, and then this one can be just obtained by the integration, right? Okay, so that means if E equal to EM is given, okay, and %x is determined now up to a factor percent x0. Okay. So that means you just take the value of this percent x0 to anything. You know, if you fix this percent x0, and then the whole wave function is fixed, all right? So this means percent mx is unique and up to a phase factor, up to a global factor. Okay. Right. Okay. Right. For example, if we just take a percent x0 equal to 1, and then this one is uniquely determined, right? Okay. So this means that the states must be non-degenerate. Okay. And actually, in the next example, we're going to show that so if they are, so the non-degeneracy, okay, so this is non-degeneracy, and the real function property of the 1D bounded states actually are related to an important property of these states, which should be consistent with our intuitive. So that is the bounded state should have no motion. Okay. Okay, so the third property, which is closely related to the previous two, okay? So bounded states, 1D bounded states has no motion. That means the expansion value of the momentum is just 0. Okay. How to prove that? It actually is pretty simple. Okay. Suppose we write this percent m is real, right? It's real function. Okay. And then we calculate this percent. Okay, let's do this one. So this will be, of course, this percent m x complex conjugate. This will be h bar of I d over dx and percent m x, right? You do integration of this x. So that is the way that we calculate this one. And remember, this one is actually the same as it's just minus I h bar percent n d over dx percent m, because it's a real function, right? Right, because percent m equals to percent m complex conjugate. Okay. Right, and then you can use the integration by part. This one also equals to I h bar d over dx percent m and percent m, right? So this is integration by part. Okay, and you find that these two are opposite, right? Okay, so that equals to minus p. Okay, so that means this one must be 0. Okay, right. So you can see that once this is a real function, actually, you can always show that the expansion value of percent is 0. Okay, so this is actually a very, very nice property of real function. Okay, so there's a few exercises for you to do to check what if the function is not real and what will happen. Okay, and now you can see that if we have degeneracy exists. Okay, and you can have two states, percent mx and percent mx, right? And then you can also show that so that means percent Hamiltonian acting on this alpha per se m plus beta per se m. You know, that equals to alpha, this one plus beta h per se m, right? This is the eigenstate. This is the eigenstate. So they give you the same eigenenergy. So that means they give you the same, you know, Em per se m plus beta Em per se m. So that equals to Em alpha per se m plus beta per se m. So this is also eigenstate, right? So that means alpha per se m plus beta per se m is also an eigenstate. So this is a very important properties of the degeneracy. Okay, so if you have two states that have, you know, that's the eigenfunctions of the same eigenvalues, and then the linear combination is also, you know, an eigenstate. And now you can check. So now I can, in general, I can put a per se plus e to I phi in general m. And this one states where these two, in general, p is not 0. So that, of course, will violate of intuition, right? So you shouldn't have a stationary state, an eigenstate of a Hamiltonian, okay, as a bounded state. Yet still have this momentum operator, expansion radius of the momentum operator is 0. It's not 0, right? So you can see that now everything is consistent. So in one-dimensional space, the bounded states must be real functions. They must be non-degenerate, and their momentum must have 0 expansion values, so that there's no motion. Okay, so these are very general properties of this 1D bounded states. Okay, all right. And there is another property which is not that obvious, but it's also quite nice, and you can check with the solutions we have obtained, and we are going to have to obtain in the future. Okay, so the number of nodes. Okay, so that means percent x equal to 0. Okay, the nodes is the location that the wave function 0. Okay, is m minus 1. Okay, so that means the ground state has 0 nodes. Okay, so this is, so no matter what's potential, so the ground state must be something like this one. Okay, so let me put in okay, like this. So no matter what's the potential, okay, so you can have arbitrary potential, and then you can have the ground state. So this is the ground state. And then the wave function, no matter what it is, okay, it must have no nodes. And then the first excited state, it must have 1 node. Sorry, this is not a good plot. Okay, so the first excited state must have okay, must have 1 node, okay, like this one. Okay, and then the third excited state, it must have 3 nodes, okay, and so on and so forth. Okay. Right. And so we're not going to prove this one, but I give you a few arguments. Okay. Right. So suppose you have a state. This is a ground. Suppose this is a ground state. Okay. This is a solution, right? Has 1 node, and then you can show that there is actually a way to reduce the energy. Okay. By change this one, by removing this node. Okay. And then you can, for example, you can change this wave function to something like this one. Okay, you can know that this is still on the left side is still solution, on the right hand side is still solution. But here, of course, it's not a solution because at this point, the wave function does not have smooth, does not have a continuous differential. Okay, but you have a way to do this. You can fix this one by just change this one slightly, make this one to be smooth. Okay, by connecting these two parts. And this one, the energy actually, this percent 0 prime. Okay, you can find this percent 0 prime x and Hamiltonian percent m prime x. So this is percent prime 0 x. Okay, dx actually will be less than the E0. Okay. So that means you have a way to reduce the energy if it does have a load in the ground state, okay? And then how about the first excited states? Okay, so this is for the ground state. And if you consider the first excited state, you can say it must have one node because you must have percent 1x, percent 0x. This one is 0, right? You know that this one has one node, has no node. I should use this one as 1. Okay, sorry. This is 1. This is 1. This is 1. So this is 2. This is 1. Okay. So the ground state. Okay, this one has no node, right? So that means you can make this one to be all positive. So if this one has no node, and then this integration cannot be 0, right? Okay, so that must have at least one node, right? Okay, and then again, if you have two nodes, you can fix it, reduce the energy. Okay, still satisfy the the orthogonal condition, but then the energy is reduced, so that means it's not going to be the first excited state, right? So this way you can, by this way you can actually kind of show the first state or the one state has no node, and then the first excited has one node, the second excited has two nodes, and so on and so forth. Okay, so this is also a very general feature of the 1D bound states. Okay, right. So there is another one. This is a special case. A symmetric potential, okay? It's not general for all potential, but this is a case that we often encountered, okay? So in this case, we say that this Vx, for example, equals to V minus x, okay? Or in some cases, you have Vx equals to V Wx, okay? Okay, just by shift. So it doesn't really matter. You can choose the origin of the coordinate system so that you have Vx equal to V minus x. So they have symmetrical potential, okay? And then you find the wave functions percent 1x actually equals to percent 1 minus x. Of course, right? Because it has no node, there must be an even function, okay? And percent 2x equals to minus percent 2 minus x, and so on and so forth. So in general, you should have percent mx equals to, minus 1 to the power m minus 1 percent m minus x, okay? So in this case, we say that this one has parity p equals to 0 or minus p equals to 1. And this one, we say that the parity okay, P equal to 1 or minus P equal to minus 1. Okay. So and so on and so forth. You can say that basically for any kind of percent mx, this will equal to, if we do the okay, and this P will equal to 0 for n equal to 1, 3, and so on and so forth. Equal to 1 for n equal to 2, 4, and so on and so forth. Okay. So the states will have alternative for parity, and we call this one even parity. This one called odd parity. Okay, because the wave function, for the first excited, third excited, for this kind of states will be odd functions, and for the ground state and the second excited states and so on and so forth, there will be even functions. Okay, we call this one even or odd parity. Okay. Actually, you could even define an operator. Okay, you can define this operator. Operator is just a change of a wave function into another wave function, right? You can call this operation is just do the inversion. Okay, you just change x to be minus x. I can say that this percent mx actually they are eigenstates of this parity. So this one, we call this one parity operator. Okay, and this is even for all the functions. They are eigenstates of this parity operator. Okay. Right. So that is another property of this, one-dimensional bounded states in a symmetrical potential. Okay. And we also say that you can actually have selection rules. Okay. Associated with this one, you have selection rules. Okay. You can find that x m that defined as percent m x percent m and dx. This one equals to 0 if percent m have the same parity. So in this case, we say that we have a parity conservation. Okay. Because we say that if you have a light, a photon, they have all the parity. So if you have a transition from one state to another state, you must keep the total parity to be conserved. Okay, because percent n and percent m, they have the same parity, so that you cannot have the transition, right? So if you absorb or emit a photon, you have to choose the parity by 1. Okay, and the same for PMM. Okay. Okay, so this one is called the parity conservation. So if we have a symmetrical potential, so you must have these selection rules. Okay, if you calculate the dipole moment or the oscillators xpm or momentum operator, if we do this calculation, you find that this integration actually must be 0 if you are calculating this between two states that have the same parity. Okay, so that means you cannot have dipole transition. You cannot have light to be absorbed or emitted between two states that have the same parity. Okay, so that is one thing that's interesting for this bounded states. Okay, so these are the general properties of the one-dimensional bounded states. Except for the fifth one, all the other fours actually are general to all one-dimensional bounded states, and the fifth one applies only to the symmetrical potential. Okay, so we have you can check this one with the solutions we had for this 1D infrared potential. Okay, And later on, we're going to learn more and more solutions, and you can check this against these rules, okay, to see, how these rules will be abided by, and what's the physical meaning. Okay, try to understand more and more the physical meaning of these rules, these properties of the one-dimensional bounded states. Okay, so let's take a break, and then if you have questions, just put it down in the chatting room. Okay. General properties of one-dimensional bounded states. Okay, so we consider already the infinite quantum well as an example, and let's consider a slightly more different example. Okay. Let's look at the finite quantum well. Okay, so in this case now we have, for example, we have a potential like this. Okay, so in this region we have V equal to 0. Or this is V equals to V0. Okay, this is also V equals to V0. So let's make this one to be symmetric. Okay, and let's now we define this as symmetric. Okay, so this is x equal to 0. Okay, right. So in this region, x less than minus w over 2. Okay, we call this one region 1. And this one is region 2, okay? And this one is region 3. So x greater than w over 2, okay? Right, so in the 3 regions, the solution actually is all quite simple, okay? But before we proceed with the solutions, let's try to have some observation or some kind of thoughts before doing any calculations. So form these habits. Just look at the problem and see what we can squeeze out of the this picture just by looking at the problem without doing much calculation. Right? And first of all, okay, we know that if the energy, if you consider energy greater than V0, okay, so that means the energy is right here, okay? So you can see that in this case, this particle can move freely, right? From left to right, or from right to left, okay? So you're going to have a continuum states. Okay, so that means for any energy, we're going to have a solution, okay? These are also called a scattering state. We're going to come back to this later, okay? Okay, but not at this moment. And then if you have energy less than V0, so you know that it will be more or less so confined with this, right? So for example, you can say that now in this case, if I have this state, and then this wave function will be, say, almost like this one, right? So if you look at the one state, but not because the potential is finite, so this will have a little bit of penetration into this one, but it will decay into infinite. Okay, so this will be the ground state, right? And probably the excited state will be something like this one. Okay, so it will be antisymmetric. So it goes like this one, and then goes to 0 at the center point, and then we come back and also goes into the barrier and decays to 0, right? And so on and so forth. Okay, so you're gonna have bounded states. Okay, so it will be symmetrical or antisymmetrical. Okay, so you're gonna have even, odd, even, and so on and so forth. Okay, right, and also you can see that there will be a penetration. Right, before we say that if this will go to infinite, percent x equal to 0 if V0 goes to infinite. Okay, right, but it's going not to be 0 because V equals to V0 is less than infinite. Okay, so that means you're going to have some penetration into the barrier. Okay, so the wave function will be kind of more extended into this barrier. Okay, and also you can see that if we look at so if you look at this solution, for example, if you look at the solution, this is effective K. Okay, the wave vector inside the well. Now, because now you're not going to have this one to be a standing wave, right? So that means you shouldn't go to 0 at this at the edge of this corner well. So you still have some space to go. Okay, so you can penetrate into the barrier. So this one will be slightly smaller, right? Because the wavelength is larger, that means the wave vectors are getting smaller. So this means the EM actually will be less than EM infinite. This is for infinite quantum well. Right. So if you compare this energy, you know, as those in the infinite quantum well, okay, so you can have the energy to be slightly different. So suppose you have this is infinite, right? Potential. So this is a ground state, right? That's something like this one. Okay, this is the first excited states, something like this one. And then this is the, okay, so this is not a proportional. So let me put a break right here. So that means this energy could be quite different. So it's not linear scale, right? So that's the states of this infinite quantum well. But suppose now you have a finite quantum well. Say the potential now is not infinite. Okay. And now this wave function, the energy will be slightly below this one because the wave function will have some probability to penetrate into the barrier. Okay. Right. So the wavelength within this quantum well will be effectively longer. Okay. Similarly for this one, so you can see that this wave function will goes to outside a little bit. Okay. So that means the energy will be lower down. And the same for the third excited states. Right, so this is something that we should expect, okay? And then of course, at a certain point, there will be no bounded states anymore, okay? Because above that energy, the states will be a continuum, okay? So this is what we should expect. Right, and then the problem is how do we solve this one? Okay, remember we have 3 regimes. Okay, right, suppose we have a state. Something like this one. And then in this region, this is the third region, this is the first region, this is the second region, okay? And in each region, the potential is just a constant. This is V0, this is V0, this is V equal to 0, okay? So for example, in this region, if you notice the energy is E, okay? And then you have in region 2, let's say, so you should have minus h bar squared over 2m d squared over dx squared. And percent x, and this one will just equals to E times percent x, right? Okay, so we already know that the solution of this one can be actually written as two terms, e to ikx plus two coefficients, e to minus I. Okay, so it's a linear combination of this one, and this k must satisfy this relation, right? So it's a real number. Okay. So this is the exact solutions. Okay. So only these two coefficients to be determined. So you have two coefficients. A2 and B2 to be determined. Okay. And now you can do the same thing for example, for the first regime. And the first regime, you should have the equation to be something like this one. And now you have one more term, that's V0 per se equals to E, right? Okay. But now you can actually move this one to the right-hand side, okay? So that will give you minus h bar squared over 2m d squared over dx squared per se x plus, equal E minus V0 per se. But remember this, you have E is less than V0, right? We consider the bounded state. So this one is less than V0. So that means this one is a negative number, okay? So the equation will be something like this one. Okay. So this, of course, is still very much like a plane wave solutions, okay? But now this one should be a plane wave with imaginary wave vectors. So the solutions will be very similar. You have A1 e to, now we have a kappa x, okay, plus B1 e to minus kappa x, okay. And this kappa, now you just put this into this one, you find that you must have kappa equals to square root of 2m, V0 minus E divided by h bar square, okay? Okay, so in other words, you can say that or I kappa times I this one, that's an imaginary, okay, wave vector. Right. And of course, similar, very similar, just the same thing for the third regime, okay? So you should have per se x equals to, say, A3 e to minus kappa x plus B3 e to plus kappa x, okay? Right, and again, you have this I kappa equals to 2m V0 minus E over h bar square, okay? Right, so altogether you're going to have 6 coefficients. Okay, A1, B1, A2, B2, C1, A3, B3 to be determined. Okay, so that is the way to find this solution, right? So you can, in each regime, the solution actually is pretty simple, but the coefficients have not been determined. Okay, so this is what we have obtained. Okay, and then what we need to do is that we needed to connect this point. So you should have wave function to be continuous, and the first order derivative should be continuous, and this one should be continuous. Okay, so you should have PHYS and PHYS prime. So you have PHYS and PHYS prime. That's the derivative. Should be continuous. Okay, so that will give you 1, 2, 3, 4 equations. You have another equations. So this one should go to 0 at the infinite, and this one should go to 0. Okay. So you have 1, 2, 3, 4, 5, 6 equations. That looks quite nice, right? So you have 6 equations. Okay. You have 6 equations at the boundaries for boundary conditions. Okay. And then you should supposedly 6 equations or 6 coefficients. We should have the solution, right? So let's try to obtain these 6 equations and the 6 coefficients for these 6 coefficients and see whether or not we can find out the solutions. Okay. So that will be the next key point. Okay. Right. So we have considered this boundary conditions. Okay. At minus infinity, plus infinity, minus w over 2, and plus w over 2. Okay. So these are the points that we should connect the wave functions, right? So let's look at the first one. Okay. At minus infinity, PHYS should go to 0. Right. And remember this one, in this region, we have PHYS x equals to A1 e to kappa x plus B1 e to minus kappa x. Okay. And now you can see that this one, for x goes to minus infinity, this one goes to 0. That's fine. But this one will exponentially divergent. Okay. So that means you got one equation. So B1 equal to 0. So this is equation, say, 1. Right, you got one equation. All right, and also you can look at another equation at plus infinity. You should have a PHYS equals to A3 e to minus kappa x plus B3 e to plus kappa x. And this one should go to 0. Okay. But again, this one is exponential decay, and this one is exponentially increasing. Okay. So you got another equation that's B3 equal to 0. Okay. That's the second equation. Okay. Right. So these two equations are very simple. Okay. So that gives you direct solutions of B1 and B3. All right. And now let's look at the boundary conditions at say this one. Okay. So that's a slightly different. Let me use different colors. Okay. So at x equals to minus w over 2, we should have the wave function PHYS x is continuous. Right? Okay. So let's write down the equation. Okay. So on the left hand side, you should have A1 e to kappa minus kappa w over 2 plus B1 e to plus kappa w over 2, right? So this is the wave function on the left hand side. On the right hand side, you should have A2 e to I minus ik w over 2 and plus B2 e to plus ik w over 2, right? So this gives us the third equation, okay? Right? Okay. And then we have the fourth equation. And this x equal to minus w over 2. And percent x should have the differentials of this one should also be continuous. Okay, so you do a differential of these terms. So that this one will give you a kappa e to minus kappa w over 2 minus bi, kappa e to kappa so b2 b1, sorry. Right, this is the differential of the wave function on the left hand side. On the right hand side, of course, you can also write down this one as A2. Now you have ik e to minus ik w over 2. And then you minus b2 times ik e to plus ik w over 2, right? So this is the fourth equation. Okay? And very similarly, you can obtain the fifth equation at x equals to w over 2. So you should have the wave function on the second region and the third region should also be continuous. Okay? So percent to be continuous. So you obtain the equation, and now in this time you should have A2 e to ikw over 2 plus B2 e to minus ikw over 2. That should equals to A3. Okay. E to kappa w over 2 plus B3 the minus, sorry, e to kappa w over 2, right? Okay, so that is the continuous equation. So this is the fifth one. Okay. And the sixth condition is at this x equal to w over 2 and percent prime, the differential of this one should be continuous. Okay, so very similarly, so you just do the differential of this both sides. So you can have A2 times ik e to ikw over 2 and plus minus, sorry. Okay, and that equals to A3, okay, minus kappa e to minus kappa w over 2 and plus B3 times kappa e to plus kappa w over 2, right? So this gives us the sixth equation, okay? So you have how many equations now we have? So using these boundary conditions, okay? So you obtain the 1, 2, 3, 4, 5, 6 equations, okay? Right? So you can put all of this one together, okay? So in principle, so you should have, you can write down this one as a matrix. Okay, now you have A1, B1, A2, B2, A3, B3. This one should equal to 0, all right? So now this one give you, so this one will be 6 by 6 matrix. Right. And now you have a nice thing to do with this. Okay. So before we write down the specific form of this one, we can actually just look at this. What kind of solution can we have? Okay. And now you can see that from this one, you immediately obtain that the solution of this one actually is pretty simple. B1, A2, B2, A3, B3. That equals to the inverse of this one times 0, 0, 0, 0, 0, 0. And this, of course, is just 0. Right. So this wave function actually, this cannot be physical, right? We shouldn't have a wave function that have all the coefficients to be 0, okay? Because this one is just per se equal to 0. So that means there's no probability at all, right? So if the probability is 0, that means it's impossible, right? So in quantum mechanics, if the probability is 0, the percent equal to 0, that means the probability is 0. So if probability is totally 0, that means it's impossible. So this is an impossible physical state. So what's wrong with this? What's wrong with this solution? Okay, that's a problem. Okay, the problem is that this one is correct only when this M has an inverse. Okay. Okay. So that means unless M has no inverse, but in that means this M is singular, right? So that means the boundary conditions needs to, a very important condition on this one, that this coefficients, the matrix, that connect these coefficients, okay? So we call this one a boundary matrix. This boundary condition matrix actually must be singular so that the solutions will exist. So of this one, there's an equation. So this is equivalent to that this matrix has determination equal to 0. Right? Remember, this one is a function so this one is a function of k and the kappa, right? And k and the kappa are functions of energy E, right? So that means from this one, you're going to have solutions of E, okay? So E must be E squared. That means not any E, can have a solution. So if you just put an arbitrary E into this matrix M, and you find that the coefficients must be 0, unless there's a special E that makes this M to be singular, and you could have a solution, okay? So that is the only possible way that you can find a solution, So this is the general way. You can see that for any bounded states, you can always do this, okay? Right? So that is the way we can check with this one. And this one actually applies not only from a double quantum well, only for quantum well. Actually, can be general. So this is actually quite general. Okay, so boundary condition leads to matrix times, you know, we call this one a PHYS, a vector that equal to 0. Okay, and this PHYS is a column of coefficients. Okay, that is a quite a general thing. Okay, and eigen energies EM will be solution. The solutions of determination of this M equal to 0. Okay, and once you have this one, so you know that if you have a set of equations that's not totally independent, that means this matrix is singular, or the determinant is 0, and you can always find a non-zero solution. Okay, and this leads to non-zero solution of PHYS. Okay, so let me give you a general case. Okay, suppose you have suppose we have a V like this one. Let's say Vx equal to, for example, something like this. Okay, right. For example, we have something like this one, and then we actually can cut this one into many small regions. Okay, so you can cut this one into small regions. Okay, within this each region, the potential is almost like a constant. And now this one you have variation, so we cut this one into many small pieces. Okay, so you know what I mean, right? So just cut this into many small pieces. Okay. Okay. So this one is the region, say 0. This is region 1. This is 2, and so on and so forth. Okay. And this is region I minus 1. This is region I. So altogether, they are I plus 1 pieces, right? So in each piece, you have the V. X is almost like a constant. Let's call this one Vi is a constant. Okay. And now we're interested in a solution. Say this is E. Okay, that's a solution. Okay, it's eigenvalue of this one. And then in each region we can define the V vector Ki. Okay, that equals to the square root of say E minus Vi times 2m over h bar squared. Okay, and now this one could be it's a real number if E is greater than this one, right? Or imaginary if E is less than this one. Okay? And the solution. Okay? The solution in each region. In the region I, okay? So you must have this percent x equals to, let's say this AI e to I ki x plus bi e to minus I ki x. Because this one will satisfy minus h bar squared over partial squared 2m partial x squared, per side. equals to E minus VI plus X. Right? It's very easy to check. Okay? So this one should be the solution, okay? And then you have boundary conditions, okay? Right. So first of all, is X goes to minus infinity, you should have percent goes to 0, okay? So that means you look at this one, so that gives immediately one equation, that is B0 should equal to 0, okay? And X goes to plus infinity, you should have percent goes to 0, so that immediately goes to AI equal to 0, okay? Right, because in this case now you have this one should be, if you take this Ki to be an imaginary number, okay, at the ith region, so you should have this one to be exponentially increase, right? And now you can also have the joint point at X equal to, say for example, Xi, and they should have a percent, and the percent prime are continuous, right? Okay. So this is the first equation. This is the second equation. So in this one, you should have two equations. So one equation is that you should have, A I e to I Ki xi plus Bi e to I minus I Ki xi equals to Ai plus 1 e to I Ki plus 1 times xi and plus Bi e to minus I Ki plus 1 times xi, right? So this is one equation. And but for the differential, you should also have another equation. So that will be I Ki A I e to I Ki xi and then minus I Ki Bi e to minus I Ki xi. That should equals to I Ki plus 1. The wave vectors is different in the next region, right? So Ai plus 1 e to I Ki plus 1 xi. And then minus I Ki plus 1 Bi plus 1 e to minus I Ki plus 1 xi. So this gives you two equations, right? Okay. Let's count the number of equations. Okay. So there will be from this is 1, 0. Altogether, you divide this one into I plus 1 pieces. So there will be I joint points, right? So there will be, so 1 at minus infinity, 1 at plus infinity, and now you have 2i at the joint points xi, right? So altogether, you should have 2i plus 2 equations. Okay. So that means you can write down these equations at, okay. Okay, this is A0, B0, A1, B1, and so on and so forth until you have AI, BI. So this is 2i plus 2 times 2i plus 2 equation, right? This is 2i plus 2 times 2i plus 2 equations, matrix. Okay, and this one is 0. So that means, and then the solution actually is standard. Okay. So the only solution is that you have this data, this determination of this m equals 0. Okay. The solution of this one will give you the discrete eigenvalues. Okay. And then that gives you, A0, B0, and AI, BI, and that gives us a percent, percent M, give us eigenstates. Okay, a non-zero solution, right? So this is the important thing that everything is determined by this boundary conditions. Okay. So the number of equations just equals the number of coefficients to be determined. So to have non-zero solutions, you must have this matrix that define the boundary conditions to be singular. So that's why the boundary states always be discrete, cannot be continuum. Okay. If you don't require, for example, if we don't require this to go to 0, okay. Suppose if percent goes to 0 at plus or minus infinity is not required. So what will happen? So you're going to have 2i equations and 2i plus 2 coefficients. Okay. So that means you have a non-zero solution percent Ex for any E, right? Okay, suppose you have you don't have this requirement, okay, and then you don't have this boundary conditions. Actually, you can have a continuum solution of this one, okay. So you can see that the reason that the boundary states are discrete is because you require 2 extra boundary conditions as infinite, so that the number of equations is the same as the number of coefficients to be determined, and then you must require this matrix, M. That comes from the continuous and conditions and also the boundary conditions be singular, so the solutions should be discrete. But if you suppose you just release one of the boundary conditions, so that you have the number of equations is less than the number of coefficients, and they should always have a solution, right? For given any energy E, so then you have a continuum, okay? So this way you have a continuum, okay? Right. So that's actually why the states above the barrier will be continuum. The energy, the states with energy below the barrier, so that's the boundary states, will be discrete. Okay. So these are quite general things. Okay. And then the question is, how do we do this one, right? How do we do this one? How to solve? Okay. So how to solve this one? So one way is, of course, numerical. Okay. So this is a lot of very difficult. So if you have, say, n times m matrix and find a solution of the determinant of this matrix, it's quite doable. Okay. So you can use a computer and to solve this problem. Not very difficult as long as you learn a little bit computational physics skills. Okay. Of course, in general, you don't have analytical formula for the solutions. Okay. So today we're going to stop right here. So next time. So I will give you some attack to the quantum well, finite quantum well problems. We don't need to use the computational physics, okay? But instead we can use the symmetry. We can use some approximation to obtain some feeling, some sense about the solutions, and compare them to the physical intuition that we should have for those bound states in the quantum well. Okay. Right. So this is what we have today. Okay. So if you have questions, you're welcome to just put down in the chatting room. Just talk. Okay.